Hey guys, so in this video today, I'd like to introduce you to a couple of new ideas. This is going to be kinetic energy, gravitational potential energy, and also work, okay? Now remember what we talked about in class is that kinetic energy is the energy of motion. And this is the energy that we really care about. This is the energy that we can use to turn different things into whatever we want, right? We can take the kinetic energy of moving water, turn a turbine, create electricity. You can take the kinetic energy of a piston inside a car and turn that into the turning wheels of your car so that your car moves forward, right? In various ways, we can take kinetic energy and we can turn it into what we want it to be. If I'm angry at my little brother, I can take the kinetic energy of this ball and I can hit his head and make him be quiet, right? So whatever you want to do, it's all about the kinetic energy. Kinetic energy is the energy of motion, and that's the energy that we want most of the time. All right, now what we're going to do is we're going to look at a couple of different situations in this video, and for each of those situations, we're going to look at it in two different ways. One of those ways is we're going to look at just the object. We're going to just look at that object and the forces that are on that object and how those forces affect the energy of that object. Okay, the second way that we're going to look at things is in a system. Generally speaking, we're going to do the object-earth system, where we group them together. Now what that does is it makes some forces, for example the force of gravity, an internal force. It makes it be inside of our system. All right, so we're going to look at those different situations. The first one is very simple, just looking at a ball here. Okay, so we take a ball, we hold it up in the air, and we release it, and it drops, right? No surprises there. It drops, it gains speed. Right? We know that. We know that as it drops, it accelerates, it gets faster. As it gets faster, it gains speed. Now, one of the things that we learned early on in this unit, we gave a definition for kinetic energy, which was the energy of motion, and we said that the kinetic energy is equal to 1/2 mv squared. Once we know that, we can see that as the speed increases, our object has more kinetic energy. So when I drop the ball gains kinetic energy. Now, why does it gain kinetic energy? Well, we can explain that in two different ways. Okay, first we're going to look just at the ball. The ball at this point in time has no energy. Okay, it doesn't have kinetic energy because it's at rest. It doesn't have gravitational potential energy because that requires an interaction between two objects. It is at rest, no energy. All right, now the ball, what are the forces on it? What are the forces on my ball when I'm holding it right here? Well, you've got the force of gravity down, and then you've got a force of me, whether it be the friction of my fingers on the side of the ball, or if I hold it like this, then the normal force. But either way, you've got the force of my hand, which is holding it up. All right, and so there we go. So when the ball is at rest, up in the air, we've got the forces are balanced, no kinetic energy, no gravitational potential energy. Okay? Now, when I release the ball, it starts to drop. Now what are the forces on it? What are the external forces on the ball? Hopefully, you said the force of gravity. Now, as gravity pulls down on the ball has some motion. It covers a specific distance. Okay? Now, one of the definitions for something that we call work is equal to the force that is exerted over the distance that it's being exerted. But this only works when the force and the distance are parallel to each other. Okay? When the ball drops, the force is downwards and the motion is downwards. So if I know the force, which is the force of gravity, and the distance over which the ball drops, I can calculate how much work this force is doing. Now, what is work? Well, work is the change in energy. So what does that mean? That means that as gravity pulls down on my ball, gravity is exerting a force doing work, which means that it's causing the ball to gain energy. So as the ball drops, we then get that the kinetic energy is increasing. The gravitational potential energy is not changing at all, because remember, gravitational potential energy must be an interaction between two objects. The external force of gravity is doing work on the ball, causing it to gain kinetic energy. Now, of course, we could calculate this, right? We know how to calculate the speed of a ball dropping. by using kinematics. You could figure out how fast it's moving at any given point along its path. And then, once you know that speed and the mass of the ball could be used to calculate the kinetic energy. Now, I'm trying not to do any calculations in this video. We're just trying to go fully conceptual here so that we kind of get an understanding of what's going on. All right, so that is how we look at the situation when it's just the ball. The external force of gravity pulls down on the ball. It speeds up because the gravity is doing work on it, causing it to gain kinetic energy. All right, now let's look at it from a different situation. We're now going to look at what we call the ball-earth system. Now, we have looked at systems before. We've kind of grouped objects together and said we're going to treat these objects as if they were one. The advantage to that is that we don't have to worry about the force between them. We don't have to worry about the interaction there. That's not going to be an external force now, right? So if I look at the ball-earth system, the forces on the ball are still the same. And they're still equal. What's different is how we're going to treat the situation when I release the ball. Okay? Right here, because we're looking at the ball-earth system, we can still say that there's no kinetic energy, right? It's still at rest, still not moving. However, it does have what we call gravitational potential energy now. Remember, gravitational potential energy is a potential energy that exists because of two objects' interaction and their position. Now, in your worksheet, we learned very early on in this unit that gravitational potential energy is equal to mgh. All right, now the h is representing the height from the floor. It's representing the distance of that interaction. Okay, that's very important for gravitational potential energy. As your height decreases, the distance between your objects decreases, and so therefore your gravitational potential energy will decrease. So when we're looking at the ball-earth system, which is the same situation as before, it's just we're now grouping the ball and the earth together, we would still say that the kinetic energy is zero, but we would say that we have gravitational potential energy because we're looking at the ball-earth system and considering the interaction between those two. All right, so I haven't put a number here because we're not calculating it, right? But there would be a value. There is gravitational potential energy here. It exists because of the interaction of the ball and the earth in the ball-earth system. Okay, there's a gravitational force there. Therefore, we would say there's gravitational potential energy because of the interaction between the two. All right, now, what happens when I drop the ball? Okay, when I drop the ball, the force of gravity is internal. So this time the force of gravity won't do work. When we talked about work before, we said that the force of gravity was an external force to the ball, and so therefore it could add energy to the system. If we look at the situation in this way, the force of gravity is now internal, right? The force of gravity is internal to the system. I still get the same free body diagram. Right? The ball still looks the same. There's still a force of gravity. However, that force is not going to do work because that force is internal. However, what will happen here, because I started with gravitational potential energy, as the ball falls, the gravitational potential energy will decrease. The amount of potential there will go down. As that goes down, the amount of kinetic energy will increase. So the kinetic energy started at 0. As it drops, that value is going to increase. But that energy has to come from somewhere. That's the big idea of what we're looking at here, is that the energy has to be conserved. You can't create energy. In this situation, the energy came from the work done by an external force. An outside force was pulling on the ball. In this situation, that is not an external force because that's part of our system. But we do have gravitational potential energy. So as that gravitational potential energy decreases, the kinetic energy will increase. So where is the kinetic energy coming from? In this situation, it's not coming from work, it's coming from the gravitational potential energy. That's the whole point of potential energy, is it's energy that has the potential to be kinetic energy later. All right? Now, that may or may not make sense. I'm going to show you one other thing real quick right now. Hopefully it will help you understand things. All right? Let's consider this in another way. The ball, before it's released, has no energy. Okay? When it's released, gravity starts pulling down on it. As gravity pulls down on it and it moves down, gravity does what we call work. Gravity says, here's some extra energy. Gravity is pulling down on it, causing it to gain this quantity that we call energy. Now, when it gains that energy has to go somewhere. Now, in this situation, as the ball falls, that energy goes to kinetic energy. It's got a little bit of kinetic energy there. It speeds up a little bit, right? Now, what happens as time goes on? Well, gravity continues to pull. Gravity says, here's some more energy. And that energy goes to kinetic energy. So now it has a little bit more kinetic energy. As time goes on, until right before it hits the ground. And at that point, it has its maximum amount of kinetic energy. And that maximum amount of kinetic energy is related to how fast it's moving. And that's literally all that's happening when we just look at the ball. Because that external force of gravity is doing work, causing us to gain more energy. All right? Now, let's look at it from a different perspective, from the perspective of the ball-Earth system. Now, in the ball-Earth system, because gravity is now internal, because of the distance between the ball and the Earth, that interaction causes my ball to have gravitational potential energy. Now, as soon as I release it, the height, remember, gravitational potential energy depends on height, the gravitational potential energy begins to decrease. And so as the ball falls, the gravitational potential energy has to go down. But what happens to that energy? If there's no place for that energy to go, if there's no forces taking that energy out, which there isn't, the only force is gravity, which is internal. So there's nothing outside to take away this energy. Therefore, it's got to go somewhere, and so it gets transferred into kinetic energy. And as the ball continues to fall, more of this gravitational potential energy turns into kinetic energy. And as the ball falls, and as it continues to fall, and it gets lower and lower, until right before it hits the ground, and all of that gravitational potential energy that was there is now transferred into kinetic energy. One piece at a time. Every bit that the ball goes down, some of that energy is transferred into kinetic energy. All right? Let's go back. Let's look at another scenario. All right. Awesome. Welcome back. So I hope that you're starting to see that energy can come from two places. It can come when work is done on a system. It can also come when energy transfers from one form to another within the system. Both ways of looking at it, both ways of thinking about it are correct. They're just different ways to see it. So what I'd like to do now is give you a second example. Okay? This one is with my friend Chewbacca. Tato Chewbacca. And what we're going to do is I'm just going to hold him right here. Okay? Now, when I hold him right here, obviously he is in equilibrium. The forces on him are balanced. Gravity's pulling down, my hand is pushing up, he's in balance. The situation I would like for us to look at here is if he starts here, and then I move him up to here, how can we describe the energy changes? How can we describe what's happening there? Okay, and so that's what we're going to talk about. Just the simple action of he's starting here, and then he ends there. Okay, that's it. Okay, so he starts here. If we're just looking at Chewie, just looking at him, forces are balanced. What types of energy does he have? Hopefully you said that he doesn't have any, right? He's not moving, so he doesn't have kinetic energy. We're not looking at the Chewie Earth system, so Earth is external, so we don't have any gravitational potential energy. He doesn't have any energy here. All right, no energy at all. Now, when I raise him and then stop there, what happens? Well, again, he's at rest. No energy, no kinetic energy. And again, gravitational potential energy is invalid because we're only looking at Chewie. Now, you may say, well, how is that possible? Because here's what we've got. Essentially, this is what we've got, right? We said that he starts down low. He had no kinetic, no gravitational. He ends up high. He has no kinetic energy, no gravitational potential energy. But didn't I do something in between? Didn't I do work? I wasn't just sitting here doing nothing. I mean, it wasn't a lot. It wasn't hard. But I did raise him up. Didn't I do something there? Didn't I accomplish something? Well, according to this, remember, work is the force times the distance, and it depends on all of the external forces. So when I push him up, I'm pushing up, and he's moving up. That means I do positive work, right? I'm pushing upwards, he's moving upwards. According to my equation here, force times distance equals work. Yes, I do cause him to gain energy as he goes up, all right? I do positive work, right? I do positive work, the force and distance are in the same direction, he goes up. Here's the clincher though. As he goes up, are there any other forces working on it? Yes, there is, isn't there? There's another force, which is the force of gravity. With the ball, when I released it, I wasn't pushing it anymore. It was just gravity as an external force doing work on it, causing it to gain energy. In this situation, gravity is pulling down on him the whole time. So what is gravity doing? Well, gravity is pulling down while he's moving up. Force is a vector. The direction matters. If gravity's pulling down and he's moving up, then the directions are opposite. That means that gravity is doing negative work. So I do positive work because I'm pushing in the same direction of the motion. Gravity does negative work because gravity's pushing in the opposite or pulling in the opposite direction of the motion. So when you put these two things together, my positive work and gravity's negative work, that means the energy doesn't change. Has the same energy it had before. Which makes sense according to the way that we're looking at it right now. Just the kinetic energy of Chewie. All right? Let's look at this from a different perspective. Let's look at it from the perspective of the Chewie Earth system. Now, in this situation, Chewie and the Earth are working together as a system. The forces on Chewie are the same, right? It's still my hand pushing up. It's still gravity pulling down. But this is different. I start with Chewie down here. No kinetic energy. But he does have a low amount of potential energy because he's down here. So this is different because now that we're talking about the Chewie Earth system, then we have to include the interaction of the two objects in our system due to that gravitational force. And so due to the distance between them, Chewie has a small amount of gravitational force when he's hanging out here. Okay, now keeping it consistent, keeping it conceptual, no kinetic energy, low gravitational potential energy. Now, I raise him up. Okay, now as I raise him up, the situation is different this time. I still have gravity pulling down and my hand pushing up, but the gravity pulling down is now internal to the system. That's part of our system. So I'm not going to include that force pulling down. So as I push him up, the only thing is my hand pushing him up, doing positive work on the system. So I do positive work. This time gravity is not doing work because it's inside the system. Forces that are inside the system, that are internal, don't add or take away from the energy. We said that in the last set as well when we were talking about the ball. So now the question is, well, if work's being done, it should be gaining energy, right? That's the definition of work. Work is the change in energy. So if work is being done, Chewbacca must be gaining energy. And when we look at it this way, when he gets up to the top, his kinetic energy is 0. Still 0 because he's at rest. However, when I look at the Chewy Earth system, that now includes gravitational potential energy. It includes the interaction between Chewy and the Earth, which means he can have gravitational potential energy. If the height increases, then the gravitational potential energy increases. So as he goes up, he will now have a higher gravitational potential energy than he had before. So I do positive work. Where does that energy go? It doesn't go into kinetic energy this time. It goes into the gravitational potential energy of the larger distance between Chewy and the Earth now. Okay? And so we've seen another situation, right? We looked at the idea when we just look at Chewy, I push up doing positive work, gravity pulls down doing negative work. Those are both external forces on Chewy. Therefore, they balance each other out, and the energy before and after is unchanged. If I look at the Chewy Earth system, then they can also store energy between that distance, based off of the distance between Chewy and the Earth. And so as I push up, I will do positive work. Gravity's internal, but it's also considered right here when we talk about the gravitational potential energy in saying that the gravitational potential energy increases. All right, now I want to go back to the blocks and show you that again. Okay, so go ahead, let's have a look at that for this situation. All right, let's have a look at energy with Chewbacca. Now remember, Chewbacca started at a low height. He had no kinetic energy, he wasn't moving. He also didn't have gravitational potential energy because remember, gravitational potential energy requires two objects in the system that are interacting with each other, causing energy to be stored inside of the system. When we just look at Chewbacca, that's not happening. We have the external force of my hand pushing up. So as I push up, I say, here, Chewbacca, here's some energy. And Chewbacca says, oh, thank you. And gravity says, nope, I'm going to take that energy. Right? I put the energy in. I'm pushing up in the same direction that Chewbacca is moving. Gravity is pulling down opposite to the direction that Chewbacca is moving. And gravity just takes away the energy that I'm trying to put in. In the end, Chewbacca is up at the top. He's at rest. He hasn't gained anything because I just keep saying, here, Chewbacca, here's some energy. And gravity says, nope, I'm pulling in the opposite direction. I'm taking that energy. Right? It's kind of like if you had a donut shop and you were trying to sell donuts. In the morning, you got all your donuts out. You got whatever flavors you want. Everything's out there. Some people start to come in to buy those donuts. They take them off the shelf. They pay for the donuts. They walk out. What happens? Well, you have donuts in the back that you made in the morning, or you keep making them throughout the day, and you just put them right back on the rack so that the rack stays full. Now, you keep doing that. People keep taking donuts away. You keep putting donuts on the shelf, right? That just keeps happening throughout the day. And what happens at the end? Well, somebody walks in and they see your shelf is full of donuts. They're like, what have you been doing all day? You're like, I've been working. I've been making donuts. I've been selling donuts. I've been doing all this work. Well, the reality is the beginning and the final look the same because the energy is the same, right? You've been putting stuff on, but people have been taking it away. When that happens, the net result is nothing looks like it's changed. And that's what's happening with Chewbacca as we push him up. He starts with no kinetic energy, he ends with no kinetic energy, even though I was doing work because there's something else that's doing negative work. All right, now let's look at the situation of the Chewbacca Earth system. Right? When we have the Chewbacca Earth system, Chewbacca starts with a little bit of gravitational potential energy. Right? He starts a little bit above the surface of the Earth. Now, as I start to push him up, I say, here, Chewbacca, here's some energy. And some of that energy initial may go to the kinetic energy, right? As he speeds up a little bit at the beginning because I'm pushing harder than gravity, so maybe I am making him gain some kinetic energy. But from then on, anytime I say, here, Chewbacca, I'm pushing you up, here's some more energy, that energy goes directly to the gravitational potential energy. Now, remember here, we now, because we're looking at the Chewbacca Earth system, we have gravitational potential energy because there's an interaction between the two objects that are both part of the system. So this gravitational potential energy is not the gravitational potential energy of Chewbacca, it's the energy of the system. Though sometimes, when we're looking at just the Earth, we may just say Chewbacca has this gravitational potential energy. It needs to be understood, though, that Chewbacca himself does not have gravitational potential energy. This is the interaction between him and the Earth causing him to have that energy. As time goes on, I say, Chewbacca, I'm pushing you up. Here's some more energy. And that then causes him to raise higher. Eventually, as I get to the top, even that kinetic energy transfers over, and in the end, he's at rest. We end with gravitational potential energy. Where did that come from? Well, that came from me doing work on the system. The only difference is that now gravity is not doing work because gravity is part of the system. And so in this situation, I do end up with more energy than I started with because I end up with gravitational potential energy now that Chewbacca is higher than he was before, but only when I make gravity internal as part of the system. All right, so our last little demo and kind of explanation for the day is the pendulum. All right, now with the pendulum, you'll notice this is just a dumbbell. Okay, an old dumbbell has got about 1.5 kilos. Okay, I did tape this green paper on here. The green paper is made out of a special polymer that decreases the friction between the air and the, no, I'm just kidding. It's just paper. It's just 3x5 cards. It's just because it's easier to see the green than it is to see the pink. That's the only reason for that. But otherwise, it'll just be a normal pendulum swinging. All right. So what we want to do here is we want to look first at the explanation of the pendulum just from the perspective of the pendulum, and then we'll look at this the idea from the perspective of the pendulum Earth system. All right. So here we go. We take the pendulum up, and we've got him pretty high. I think you should be able to see him on the end of the screen there. We release the pendulum. The pendulum swings over and more or less swings back to about the same height that it came from. It'll be a little less because we do have some friction. It's rubbing against the ceiling, the string is. So we're going to lose a little bit of energy. Friction's doing negative work, right? Friction always works opposite the direction of motion. And so it's always negative work, always losing some energy. But for the most part, when I drop it, it will more or less come back to the same height that it came from. Now, why? Why does it do that? Well, let's look from the perspective of the pendulum. The pendulum is right here. At the beginning, it has no kinetic energy. It has no gravitational potential energy. Remember, gravitational potential energy requires the interaction between the pendulum and another object in the system. It's the potential of the system. It's not the potential of the object. Okay? So here, the pendulum is here, no energy. Now, when I release it, gravity is pulling down on it. If gravity is pulling down on it and it has some downward motion, remember when we talked about the circular rides, we were talking sometimes about the component of the force that's in that direction, or the piece of the force that's in that direction. Same thing here, right? As it goes down, gravity is pulling down as the object moves, at least partially in the downward direction. So as gravity does that, the object is moving down, gravity is pulling down, gravity does positive work. That means that the object has to gain energy. And if the object gains energy, well, what type of energy is that? Well, it's gaining speed. It's gaining kinetic energy. So it starts with 0 energy, and as it gets down to the bottom, it now has kinetic energy because of the positive work done by gravity. Now, you may say, well, what about the string? There's another force there. Well, you should ask that question. That is an external force, isn't it? But remember that the external force only does work if the force has a piece that's parallel to the direction of the motion. Anywhere where this is, right here, the mass is moving down this way, okay? You may notice that the string is perpendicular to that. Now, when an object is perpendicular, when two lines are perpendicular, then no component is parallel. There's no piece of that that's parallel. And because it's perpendicular, not parallel at all, there's no piece of it, that means that the tension won't do work. It won't cause your object to gain or lose energy. Now, this should make sense with the rides like the Gunslinger and the Area 51, where we talked about a force pushing towards the middle that didn't cause the object to speed up. It didn't gain kinetic energy. It just maintained the energy that it had. And so a perpendicular force will not do work. There can be other forces. Here, the force of gravity pulling down doing work, causing it to gain energy. But in terms of the force of the string, not going to do any work, not going to cause it to gain energy. This is also going to come into play when we start to look at the roller coasters and things like that, because the cart will be moving down the track, and the normal force of the track will always be perpendicular, meaning it won't do work. It won't cause energy to be added in or taken out, unless there's some friction, which does. If the cart's moving this way, friction is the opposite direction. Now we've got a parallel comment, but that's not the normal force of the track. It's not the tension of the string. It's the friction that's involved there. All right, so that's how we would look at it from the perspective of the pendulum. As the pendulum swings up, as it goes up, it now has some upward motion with gravity still pulling down. Now gravity's in the opposite direction. If gravity's in the opposite direction, remember, opposite direction means it's going to do negative work. It's going to cause my pendulum to lose energy, which is why as it swings up, it loses kinetic energy and therefore loses speed. It slows down until all of that kinetic energy has been taken away by gravity, and then it starts swinging down again. That's the perspective of the pendulum. Now let's look at the perspective of the pendulum Earth system. All right, so pendulum Earth system. Now at this point, because I'm talking about the combination of the pendulum and the Earth, they now have that interaction because of the gravitational force between them. The Earth pulls on the pendulum pulls on the Earth. There's some energy stored there. When I release, they should come together gaining energy, gaining kinetic energy. So we say they have gravitational potential energy in the system between them. So I start up here with a high amount of gravitational potential energy. When I release it, it now goes down. As it goes down, the gravitational potential energy decreases. Where does that gravitational potential energy go? Well, it's turned into kinetic energy. So as the gravitational potential energy goes down, the kinetic energy goes up. No work is being done. Gravity is internal. The string is perpendicular, doesn't do any work. There are no other forces that could cause the system to gain or lose energy. The energy is just transferred from one form to another. Okay, as it swings up, the same thing. We start with a low gravitational potential energy, but a very high kinetic energy. That's the fastest that it goes down at the bottom. And as it swings up, it starts to slow down. Well, why does it slow down? Because that kinetic energy is being turned into the gravitational potential energy, because the distance between the mass and the Earth is increasing. And that's your mgh. As the height increases, the gravitational potential energy is increasing. Therefore, you must be getting that energy from somewhere, in this case, from losing the kinetic energy. Okay, let's go ahead and look at it from the perspective of the blocks, and then we'd be done. Now, when we look at the pendulum, remember the pendulum by itself does not have gravitational potential energy. It needs to be part of a system in order for that to happen. So the pendulum does not have gravitational potential energy. When I hold it at its highest, it doesn't have kinetic energy. It is at rest, so therefore no energy here. Now, as time passes, when I release the pendulum, gravity is pulling down on it. When gravity is considered an external force, gravity does work. Gravity says, here, have some energy. Now, where does that energy go? Well, the object is going down, the pendulum's going down and gaining speed. And so that energy becomes kinetic energy. As long as the pendulum is swinging down, gravity is doing external work on it, saying, here's some more energy. And the object speeds up. Kind of like the ball. When gravity is pulling down on the ball, gravity was an external force. It was causing energy to be gained. And by the time we get to the bottom, the object has its maximum kinetic energy. Now, once it's at the bottom, it starts to go up. And now that it's going up, it's moving up and gravity's pulling down. Now that gravity's pulling in the opposite direction, gravity says, you know what, I'm working against you now. I'm going to take that energy away. That's mine. As it continues to swing up, I'm going to take that energy away. It's mine. Until all of the kinetic energy that was gained due to gravity doing work on it is now lost due to gravity pulling in the opposite direction. Gravity's pulling down, the object's moving up. Okay? Now, what happens when we look at the pendulum Earth system? Well, that's a little bit more interesting. When we look at the pendulum Earth system, it starts with gravitational potential energy, right? It has gravitational potential energy because there is now an interaction between two objects in the system. So it has some height. It's at its maximum height. Now, as it starts to swing down, what happens? As the pendulum starts to swing down, there are no external forces other than the string, which is perpendicular, and the perpendicular forces don't add or take away energy. They don't do work. So the only thing happening is we have the pendulum that starts to go down, which means that it's going to lose some of this potential energy that it has due to its position. Now, if there's nothing taking that energy away, the energy has to stay here. So therefore, it goes to kinetic energy. As the pendulum drops, more and more of that energy transfers over to the kinetic energy. As it drops further, continues to drop until we get to the point where the pendulum is at its lowest point. Now, there's probably still some gravitational potential energy there because of its position, but most of that energy has transferred over to kinetic. Now, as the pendulum starts to swing up, the height starts to increase, so this needs to go up. Well, where is this going to get its energy from if there are no external forces putting the energy in? Well, it's going to take it from here, from the kinetic energy. So it says, all right, you can have it back now. As it starts to swing up, the height increases, the kinetic energy, the speed decreases until we get back up to the maximum height that we started from. And once we're back at the maximum height we started from, the pendulum will be at rest again at the same height because it needs the same energy as before, unless energy is being lost. And with this situation, it's not. If there's friction, then yeah, maybe as we go through, friction says, I'm going to take that energy. And so maybe it won't get quite as high as it did the first time. But if we say no friction, no energy lost, then the energy that we start with should be equal to the energy that we end with. All right, that's all, folks.